Hello everyone, my name is Fan from the Gas Network. Today I will present about zkSwap, an Oracle-based zero-knowledge automated market maker for SPL zk tokens. This presentation is for Solana Riptide Hackathon submission. So overall, the presentation had seven sessions. Sorry. In the first session, I will have a brief of SBL zk token and the need of zkSwap. In the second one, we will learn about product constant and how it would work with the zk token. In the next three, I will propose the main protocol of Oracle-based zero-knowledge AMM. Also, I will do a benchmark and a demonstration in this session number 6. In the last one, I will examine the current pitfall of the protocol. In August 2021, Solana Labs introduced the SPL token standard for privacy named SPL zk token. The protocol is based on the more updated research of zkSwap. Mostly is about brain proof. Thus, proposal open the chance for new application like confidential transaction, a privacy preserve e-voting system. However, the new standard may not be compatible with the current DeFi system due to the difference of computation, of course. zkSwap is our attempt to build an AMM that employs the SPL zk token standard. This AMM could be a vital component for the next privacy finance system. The protocol introduced an Oracle-based AMM. The Oracle is a node that will provide anonymous data like price or knowledge proof for swapping or providing liquidity. Fundamentally, the protocol still has similar functions of a swap while securing the privacy of user. To build an AMM, the product constant is an essential factor that maintains the pricing curve between two tokens. Unfortunately, we cannot directly implement the product constant on SPL zk token because of the confidentiality of transaction. However, there are some property that we can use to develop the AMM with correctness. The product constant say that in any swap, the product of preserves must be invariant. That means if the token A increase gamma times, then the token B must decrease gamma time in amount to hold the product constant. Additionally, gamma could be derived from the price change. That's equal to the square of gamma. We can note this property for swap function in regard to deposits and withdrawal by setting up the return token, the return LB token equal to the square root of A times B. We no longer need to care about the proportion of pool shares. It's obvious that the computation of gamma, we need the information of current price, right? That's the reason every pool will have an oracle alongside. Generally, when a pool initializes, an oracle will start up and send the private information of the pool. Every time Alice needs to execute a transaction that requires some data, she had to query the data from Oracle. However, the data that Oracle provides is anonymous data. It won't reveal any identity data like parent, reserve, or order. In high concept, to swap, Alice gets the price from the Oracle, compute gamma, and compute gamma from her design next price. send the price to the oracle and receive back zero knowledge proof for the transaction. Deposits is easier when Alice doesn't need to interact with the oracle. Alice can compute the number of LB based on the number of token A and B she would like to deposit in the pool. Then she can construct the proof and then submit it. Withdrawal is similar to the deposit. First, to understand how Alice could construct a proof for her action, we will learn a foundation that we can build more sophisticated proof on top of them. Peterson commitment and twisted algorithm encryption is used in the SBL ZK token. The beauty of them is that they are additive and linear homomorphism. In short, we can sum two commitment or cipher the same as we sum the secret inside of them. In multiplication proof, the proof can prove Peterson commitment C3 here is a scalar multiplication of C2 by a secret X to a verifier without reviewing X. Why the verifier know the commitment of X as C1 right here. In the Peterson commitment equality proof, the proofer can prove to a verifier that C1 and C2 is two different commitments of the same secret X without reviewing X and or blinding factor R1 or R2. Moving on to square root proof. Square root proof is a consequence of a multiplication proof and Peterson commitment equality proof. The proofer can prove to a verifier that C1, C2, C3 a commitment of X, Y, Z respectively, where X times Y is equal to the square of G's. One of the more important proof that zkSwap heavily relies on a hybrid equality proof called CT1 and CT2 is the encryptions of X. CT1 is generated by the knowledge of secret key S right here, while C2 is constructed by the knowledge of the public key R2 right here. To understand the context, let's consider an example that Alice needs to send token to Pop. In order to prove that she doesn't cut money from the air, she needs to generate CT1 encryption that she will subtract to her balance, which she knows exactly the secret key, and CT2 encryption that she will add to Pop's balance, which she only knows Pop's public key. That's the scenario to describe the hybrid equality proof. Based on the foundation, now we can construct the proof system for the AMM. It has three proofs, including product constant proof, deposit proof, and withdrawal proof. Recall that to execute a swap transaction, Alice must compute her gamma and send it to the oracle. The oracle who knows the secret key of the pool treasuries and Alice public key can generate the proof for first transferring token into the pool on the bid side. The second, returning the token to Alice wallet on the ask side. The last one is maintaining the product being invariant. So Alice just needs to verify the proof that return from the oracle for correctness and soundness. Then she can submit them to run the transaction. Deposit and withdrawal are similar. Alice can compute A, B, and LB, where LB equal to the square root of the product of A and B. Then she generate the equality proof for token in and out, and a proof for square root relationship of A, B, and LB amount. To the benchmark and demonstration, we can see that the maximum proof is equal to 1280 pi, which is, I suppose, is succinct enough to run on chain. Even though the SBLZK token is not ready on chain, we developed an off-chain ledger that simulates the ZK token. Then we can build zkSwap on top of it. So we can go through a quick demo right here. So here we got the UI for the zkSwap. Let's say we can do the deposit flow first. So when it's not different from the other application like Uniswap, when I have to input the number of token I would love to deposit in, and then it will show the number of LB I will receive back for my share in the pool. So I got 100 share for the liquidity I have deposited in the pool. I can withdraw, let's say I will withdraw back my 100 share. So you can see that this will return 2 token per 100. Okay. Move to the swap. The UI of the swap is quite different from Uniswap or Curve or any other swap because the core mechanism for now is quite different compared to the others. Instead of input the amount of selling token or something, the user is required to input the next desired amount. Let's say I want to move the current price from 1 to 0.9, then I have to input 0.9 under the hood by the next price and the current price. My device will compute the gamma and then send it to the oracle. The oracle, based on the gamma and the current state of the pool, will compute the selling amount and buying amount, and then send it back to me with the proof. By the proof, I can execute the transaction with correctness on chain. So the current price is moved to 0.9 as my design. The current protocol had a pitfall in withdrawal proof. For example, Alice can generate a valid withdrawal proof by input LB equal to 0, A equal to 0, and B equal to 1000, for example. By the proof, Alice will pay nothing but receive back 1000 B token. So by the attack, the type attack, Alice can drain a token of treasury. To fix this, the protocol needs an additional proof for withdrawal. The proof will prove that the amount of withdrawal is proportionally equal to the share that will be burned. That's all about the zkSwap. Thank you.